Okay, hi everybody, and welcome to another edition of the Point Distributions webinar. Before I introduce our speaker today, let me just mention that this week we have two talks. So this Friday we have another talk by Matthias Sonnleiter, and today our speaker is Tetiana Stepaniuk, and she'll be talking about estimates for the discrete energies on the sphere. So please, Tetiana, the screen is yours.
Thank you very much, Damir. I would like also to thank you, the other organizers, Ryan and Sasha, for organizing this nice seminar. And it's nice to meet people, at least online. The main subject of this presentation will be the positive definite function of the form one, where which are represented in the as ultraspherical expansions in the terms of generalized Legendre polynomials with some non-negative coefficients. This ZDL is a dimension of spherical harmonics of degree L, and psi of L is some non-negative coefficients. As this psi of L, we will consider some particular cases, but also some more general cases with some conditions on this function psi. Then for some endpoints on the sphere as D, in the space RD plus 1, I will consider the discrete energy of the following form. And according to this positive definite function K psi D, and also the minimal discrete energies of endpoints on the sphere, where the infimum is taken over all of the sets xn. And we'll denote the minimal energy by calligraphic M. It should be noticed that this energy is closely related with worst case numerical integration arrow, and in this presentation we will talk, and from estimates to numerical integration arrow follows the estimates for such kind of energies. And in the presentation will be both estimate for worst case arrow and for such kind of energies. So I will remind some definitions. So we have some Banach space B of continuous functions with some norm, and we will approximate the numerical integration rule with some weights such that the sum of all weights equals 1 by integral of this continuous function. And supremum of all function f from this space B such that which belongs to unit ball of space B, we will call it as worst case arrow in the space B. And by Q or without omega, we will denote the equal weight numerical integration rule. It is possible the worst case arrow in reproducing kernel Hilbert space B can be written as computable expression as double sum as square worst case arrow equals double sum of omega I omega j with some k by tilde, where kb is a producible kernel in space B, and KB tilde is producing kernel with 0 term omitted. And from this equality, we can see that indeed the estimates for worst case arrow gives the estimates for the energies of the form on the first page. I will also recall what means reproducing kernel Hilbert space. It means that there exists some kernel KB such that which has the following properties. It is symmetric. It means that a k of xy equals KB of yx. It belongs to the space B. And the set property is reproducing property, the scalar product of function f with reproducing kernel KB gives a function f. It means that the scalar product recovers the function f for any f in the space P. This equality is easy to prove. Indeed, the worst case, the squared worst case error in the space B can be written as supremum of all function B from the unit ball as space B as model squared of scalar product. And it is easy to see the scalar product f with the first sum gives us numerical integration rule, and scalar product function f with integral, we can put f under integral, and it gives just integral of this function f. And using the extremal case of Cauchy inequality, we will get that it just equals squared norm of the second term. And using elementary calculation, we got that this squared norm equals such three terms. And here it's easy to see that all these integrals are the same, and the sum of the weights omega I equals 1. So here we have minus 2 integrals plus 1 integral, and we will have minus 1 integral. So we'll have the sum minus 1 integral, which we can write as double sum omega j omega I with k base tilde, where k base tilde without 0 term, and actually this integral there is a 0 term. By YLK, D we denote the collection of real spherical harmonics in the sphere as D in the space are D plus 1 of degree L, and where the D of L is the dimension of spherical harmonics of the degree L. And also we will use that by lambda L, which equals L multiplied by L plus D minus 1, we will denote the eigenvalues of Laplace-Beltrami operator on the sphere. Then as class B, we will consider a few classes. The first class is the Sobolev class HS. It consists for all non-negative S as function with a finite norm, where F with hard Laplace Fourier coefficients of the function F. Here we have his coefficients 1 plus lambda L to the power S. And for S larger than D over 2, this space, Sobolev space HS, is embedded into a space of continuous function. And the reproducing kernel KDS in this Sobolev space is given by the following formula. So instead of our psi, we will have 1 plus lambda L to the power minus S. With Peter Grabner, we considered the space HD over 2 gamma, which defined for gamma larger than 1/2, a set of all functions whose Laplace Fourier coefficient satisfies the following equality. The difference between Sobolev and this space with HD over D over 2 gamma, that here S should be larger than D over 2. And in our space HD over 2 gamma, we put S equals D over 2. But of course, to have the embedding into space of continuous functions, we put some extra log term. And for gamma larger than 1 over 2, this space is embedded into space of continuous functions. And the reproducing kernel KD gamma in this space is given by the following formula. So instead of psi, we would have like 1 plus lambda L minus D over 2 log to the power minus 2 gamma. ZL. And the generalized Sobolev space HC consists of all functions such that the following norm is finite. Here we have some function psi of L. And to have embedding into space of continuous functions, we need that this condition holds. So sum from L to infinity psi of L, that the L should be less than infinity. And the reproducing kernel KPCD of the Hilbert space is given by following formula. So it's just the kernel which was mentioned on the first page. And of course, in some particular cases, when this psi, it can be like Sobolev spaces, or this space with our space with logarithmic term. This space HPC is a producing kernel Hilbert space because it's easy to see that the kernel KPCD has the following properties. It has symmetric, it belongs to the space, and it has a reproducing property. I would also need some definitions of spherical T designs. So I'll just recall some information about spherical T designs. Spherical T designs on the unit sphere SD in this Euclidean space D+1 are called the set of endpoints such that the numerical integration rule with nodes in these points integrates all polynomials P with degree less equals T exactly. It means that such property holds, where n is number of points and T degree of spherical T design. We will also use the well-separated point set. A set of n points is called well-separated if there exists positive constants such that the minimal distance between two distance points is larger than this constant c divided by n to the power 1 over d. And should we notice that a definition of spherical T design is equivalent to the following formula. It means that for Legendre polynomials of degree from 1 to t, the double sum of xy from xn gives us just 0. This formula is just a direct consequence from the addition theorem for spherical harmonics. If we substitute instead of Legendre polynomials this sum, we can use directly the definition of spherical T design. The question about relation T and N during long time remained open. The spherical T design was introduced in the paper by Desalte, Gossels, and Seidel in '77. And in this paper, they also established some lower bounds for N in the terms of T. But these lower bounds can be achieved only for some very small values of T. In '84, Seymour and Zaslavsky showed that for every T larger than 1, always exists a spherical T design, but they're given no connection between T and N. Then later, Kurever and Meyers conjectured there always exists spherical T design with n of order T to the D points. Also, this conjecture was made in works of many other mathematicians. And finally, in 2013, Bondarenko, Karachenko, and Vizovska solved this long-standing problem and shows that for d larger equals 2, always exists constant cd dependent only on d such that for every n larger than this constant multiplied by t to the power d, always exists spherical T design with n points. And later in 2015, they proved the similar results, but for well-separated spherical T design. So if for each d larger equals t, exists some positive constant c and lambda, depending only on d, such that always exists the spherical T design, which has a separation property that distance between two distinct points is larger than this separated constant lambda d multiplied by n to the power minus 1 over d. And on basis of this result, we will use that n have order t to the power d. Now I will go back to the worst case error. This worst case error for Sobolev spaces, it probably remains definition for Sobolev spaces. So Sobolev spaces is a space of all functions which has such finite norm. Here we have lambda L to the power S, and lambda L has the order L squared. So it was showed that for S larger than d over 2 exists some constant such that for every endpoint spherical T design, the worst case error in Sobolev space less than constant divided by T to the power S. This theorem was proved for the case S equals 3 over 2 and for sphere S2 by Hesse and Sloan in 2005. And for the case of S larger 1 and D equals 2 in the Hesse and Sloan 1 year later. And for all, for the D-dimensional sphere, it was proved by Brauchert and Hesse in 2007. For the lower estimate, it was shown that for S larger than d over 2 exists a constant such that for every endpoint configuration xn always holds the estimate, the following estimate, that the worst case error in the Sobolev space HS is larger than constant divided by n to the power s over d. Of this result for this for the sphere S2 in three-dimensional space was proved by Hesse and Sloan in 2005, and for d-dimensional sphere was proved by Hesse in 2006. And from this result and from previous theorem, we can see that for the Sobolev space, well separate the spherical T designs provide the best possible order, because here we have the order n to the power minus s over d. And here we can, instead of t, based on the result of Vazovska and Bondarenko-Radchenko-Vazovska, we can put also n to the power 1 over d will have the order 1 divided n to the power s over d. For the case hd over 2 gamma, it was showed that for d larger than 2, gamma larger than 1/2, and if xn a well-separated spherical T designs, which has t to the power d points, exists some constant such that the worst case error in the space hd over 2 gamma will be less than some constant multiplied by n to the power minus 1/2 and log n to the power minus gamma plus 1/2, and the same estimate from below, from another constant and n to the power minus 1/2 log n to the power minus gamma plus 1/2. So from here we can see that for worst case error for well-separated spherical T designs have the order n to the power minus 1/2 log n minus gamma plus 1/2. We also showed the lower estimates that for d larger than 2, gamma larger than 1/2, and if q is arbitrary and point q Bichy rule, always exists constant cd gamma such that this worst case error will be larger than n to the power minus 1/2 log n to the power minus gamma. But with comparison with previous result, we still have gap with a square root of log n. Here have log n to the power minus gamma, and here minus gamma plus 1/2. And, as a consequence from the following theorem, we get that the discrete energy the discrete energy using reproducing kernel of Sobolev space has the following estimate, that 1 plus some constant divided by n to the power s over d from below on the upper and below estimate. And for the reproducing kernel of the space HT gamma, I will have the following estimate for the minimal discrete energy. We'll have the following estimate: the 0th term log c to the power 2 gamma, and plus some constant n to the power minus 1/2 log n minus gamma plus 1/2, and but a bit with some gap from below. Again, 0th term plus a constant multiplied by n to the power minus 1/2 log n to the power minus gamma. For the generalized Sobolev spaces, we will have some condition for the coefficients psi. And for this, we consider two set of functions. By theta d, we denote the set of monotonically non-increasing functions such that exists constant lambda larger than d, such that function t to the power alpha psi of t almost decreases. It means that exists some constant chi such that the following inequality holds. It's not decreases, but almost decreases, means with some constant decreases, as where 1 less than t sub 2 and less than t sub 1. And also we denote we will consider another set of functions b. By b, we denote the set of positive functions psi of t monotonically non-decreasing for t larger than 1, such that exists a positive constant k, such that psi of t divided by psi of 2t less than constant is bounded above some constant. We need the condition theta d. Condition theta d allows provides that our space HC will be embedded into space of continuous function, because it means that the coefficient of this space will decrease a bit faster than t to the L to the power d, L to the power minus d, and it allows to have convergent series. This coefficient b, it's actually it gives this condition actually means that function psi somehow are bounded decreasing faster than some power function and decreasing slower than some power function. But it still allows to have some gap between this power, to have not only power functions, but for example, to have some function. Of course, we will have also power functions, t to the power minus s, for example, but we will have also a function like 1 divided by t plus 1 to the power s, log to the power alpha of t to the s. And or we can have this log as in nominator. Here is a bit to move the constant. And we can write down the many other examples of functions psi. For example, we can put more log of log or something, yeah, to have more examples than only power function. And I would like to say that also instead of this constant 2, we can write down actually any constant c, which is larger than 1. This condition will be the same. The condition will be equivalent. Then we show that if d larger or equals to and function psi belongs to the b and theta d, then the minimal discrete energy of this kernel psi d is less than psi of 0 plus some constant multiplied by psi of n to the power 1 over d. And it's also larger than psi of 0 plus some constant multiplied by psi to the power n to the power 1 over d. It should be noticed that if instead of psi we consider our power function, we got the results for known result for Sobolev spaces. but cannot get the result for our spaces with gamma, because this condition theta d is a bit stronger and does not allow it to have some very boundary cases. This theorem follows immediately from the two lemmas. The first lemma, if d larger equals to is fixed, psi belongs to b and belongs to theta d, and if xn is a well-separated spherical T design with where n have the order t to the power d, then exists some positive constant c such that the discrete energy minus 0 term is less than this constant multiplied by psi of n to the power 1 over d. With this we have like upper estimate, and a lower estimate we can show that if with the same condition, if c belongs to the b and belongs to the theta d, and for xn is arbitrary in point seconds, then exists some constant cd such that the energy minus 0 time will be larger than constant multiplied by psi to the power n to the power 1 over d. This the lemma 2 follows immediately from result Dmitry Bilek and Van Dye, and for the case when psi belongs to b, it's the lower estimate is exact for the order. If we take an example of function psi, for example, 1 divided by k to the power 1 to the power s, and divided by log to the power alpha of k, then we have that the minimal discrete energy will be equals log to the power minus alpha c plus some constant divided by n to the power s over d divided by log to the power alpha n. From this result, and of course we can have the same for the Sobolev spaces. Then I would also say a few words about jitter and samplings. So let we consider some real AHA will be a real regular partition on the sphere. That it means we divided sphere into n equal spots, such that the intersection of two regions equals 0, and the area of each region equals 1 to the power 1 over n, and also the diameter of each region is less than some constant multiplied by n to the power 1 over d. And in each of this region, we will choose the point x. We will choose randomly the point xj in each of this region. By sigma j, we denote the restriction of normalized measure n sigma to each of this region, and such that sigma j star will be a probability measure, because mass of each, the mass will be 1 on each piece. And we consider energy integrals with respect to this probability measure sigma j. This energy integrals of the following form. In the work with Peter Grabner, we showed if KD is continuous function, which is defines in the same way as was in the beginning of the talk. Then there exists a positive constant CD such that for this energy integral, the following estimate holds. And we will apply this estimate for for some particular cases. From the previous theorem, it follows that for reproducing kernel of Sobolev spaces, the following estimate holds. Yeah, it means if S larger than d over 2 and less than 1 plus d over 2, this energy integral is less than n to the power minus 2s over d. And if S equals 1 plus d over 2, it less than n to the power minus 1 minus 2 over d log n. And if S larger than 1 plus d over 2, it has order n to the power minus 1 minus 2 over d. And actually in this, in the first case, when S is large d over 2 and less than 1 plus d over 2, the jitter sampling give us quite good estimate. It give us exact by order estimate, and in the rest a bit worse. For the reproducing kernel of the space HD over 2 gamma, with gamma larger than 1/2, from this theorem, it follows that the energy integral is less than n minus 1, n minus 1 log n to the power minus 2 gamma plus 1. And for this space HD over 2 gamma, this estimate is exactly by order. And actually, it's quite natural because it's a more boundary case, and here jitter sampling gives good estimates. And for a reproducing kernel of Sobolev space H psi, we got that the following estimate holds. And we will try a bit to simplify these expressions. So it means that for energy of the kernel capside T minus 0 term, it's less than the following expressions. And with some condition on, if in some more conditions function psi, we can simplify it a bit. In particular, if psi belongs to B and also belongs to theta sub D plus 2, then this energy minus psi null will be less than some constant multiplied by n to the power minus 1 minus 2 over D. And if psi belongs B and belongs theta D, but minus theta D plus 2 minus some epsilon, then it will be less than some constant CD multiplied by psi of n to the power 1 over D. And actually, this case is somehow analog of this case, whereas it's more close to this. In the case of smaller smoothness, jitter samplers give us good estimates, which are exact for the order. And this case is case with more higher smoothness. Actually, it's all I'm trying to say. Thank you for attention.
So thank you for your very nice talk. So are there any questions? Then perhaps let's start with me. Just let's talk about these functions psi, right? They are decreasing, almost decreasing with t to the power alpha. Now you obtain essentially for every function psi another constant. So do you know any dependencies on these constants to the functions psi? So are they?
Which constant?
You have these constants on energies for the Sobolev spaces with the psi's, right?
Yeah.
And if
yeah. You mean this constant, right?
Exactly. Yes. Now, if do you have any idea how these constants depend on psi? So if you have a small change of psi, does this affect these constants in a very small way? Can you say they are, I don't know, if psi 1 is less or equal to psi 2, can you say something about the constants? Is this order preserving?
I didn't write the estimates for this constant, but okay. This constant, they actually, I think it's possible to write down some estimate probably at least.
Yeah, not just
These functions
estimates.
do not depend on n, they just depend on d and psi. And
Yes, yes. I just thought it might be interesting to know how they depend on psi. So if you have, for instance, psi 1 is less or equal to psi 2, perhaps the same is true for the constants or reversed order or anything like this. But yeah, it's apparently nothing that you have been looking into. All right. Are there perhaps any more questions?
Yeah, I have a quick question. So I'm trying to compare, so could you go to the next slide? So that's 26, so equation 26, right? So this is essentially saying that if you take so if your function psi is in this theta d, then if you take a separated spherical design, then that gives you optimal error. Right, and I'm trying to compare it now to jittered sampling. So do I understand it correctly that in jittered sampling, just being in theta d is not enough? You require...
Yeah, it's if for jittered samplings, when the smoothness of function psi is not high, quite low, then the jittered samplings gives good estimate.
It would give the same estimate then, right? But it was the same.
Yeah, it's the same estimate. But for a bit, but it's just quite a quite narrow smoothness. But for higher smoothness, it's not good enough.
So it's not. So you know that it's not good enough for higher smoothness, right? It's not just that it's not proved. You know it's not good enough. You know that you get.
Oh well, it's not proved, but at least it follows so that.
Okay.
And actually, jittered sampling is somehow like expected value, and it was shown that for expected value, it's yeah.
Okay. Okay. Thank you.
Okay.
So I have a question. So you certainly know about this Ataya, Marzo, Ortega, Serdar paper where they extend separated designs to other manifolds.
Yes.
So so how much of this would apply to their context? How much of this of such smoothness classes would apply to their context?
Yeah, I think it's also possible to apply. I just started from the sphere just for. And also, it's I consider when psi belongs to B, but there are also another smoothness of psi, which should be considered separately, but they need like more techniques, or like just to sense a bit more.
Yeah, this condition on psi is interesting. So I don't know if you're aware.
There are different conditions of psi. This one, for example, we can consider also when psi are infinitely differentiable, and also like a difference with different cases of decreasing this function psi. This one is one of when it's decreased approximately as power function, but for it's also will be interesting to consider for other cases, but it will be probably more difficult.
Yeah, so as a curiosity, I'm trying to find this slide. Here it is. So your slide with equation 21. So that would be a couple of slides back. Well, yeah, for some reason, okay, for some reason okay, yeah, seems to work. No, it doesn't work again. Yeah, well, so anyway, on this slide with equation 21, you state, yeah, so these are the examples of size. So this looks, yeah, exactly. So this looks, so there is something called Karamata theorem, which characterizes functions of psi such that the ratio like this. Okay, so imagine replacing 2 with yeah,
we can replace here 2 with any constant which is larger than 1.
Right. So
it's the
okay.
Same condition.
Yeah. So there's a class of functions for which if you put something that goes to infinity in place of 2, and that limit exists, right? So you can characterize these functions exactly, and that's something called functions of regular variation. So that's I think in your context it's more of a curiosity, but maybe something that would be interesting to
yeah, it's
join here. Yeah.
Actually, this can take, in my PhD thesis, I considered different classes of smoothness of, actually with this psi, but with respect to Fourier series of trigonometric series and with some approximation by Fourier sums, best approximation. And then we have a quite wide spectrum of function psi, and this one of these cases.
I see. Yeah. Okay. Yeah. Very, very interesting. The conditions themselves. Yeah. Thank you.
Oh, thank you.
Any more questions? You're welcome to use the chat.
Stop the recording then, and in
Yes,
case anyone
please.
wants to ask questions off the record.
Exactly, let's do this.